All right, so welcome back. Welcome back to this channel. So in the last video, of course, we have learned about Wasserstein GANs, right? I think yeah. So in this video, we're going to look at we're going to study a new paper, Pix2Pix. It's a paper that is published at 2018, right? Yeah, 2018. So it's a very good paper. Just read it. I'm going to go through some parts. We'll just go through it. Maybe let's see if we can find anything. Okay, so the paper name is, as you can see here, image to image translation with conditional adversarial network. So the basic idea is, given an input image, given input image, give output generate an output image, right? So whatever problem that is, so you can solve different problems by changing the training data set. For example, we have many application like this, labels to see street scene. So for example, you have these labels, some uh, segmented images. You know about segmentation, right? Hopefully, if you know about segmentation, it's actually nothing but having these like colored elements, just coloring every pixel, just having those shapes come out. I mean, there are many algorithms to do that in computer vision. So the idea is we have to reverse engineer. We have to take this image and generate a realistic image that looks pretty real. I mean, this image looks pretty real, right? Right? You could see that maybe it is in motion or something. So yeah, I mean, that is the idea. You should take images like this and generate the images. That is one. Labels to street scene, aerial to map. Given a, let's say, satellite images like this, just generate like a Google Map interface, right? Just generate an image like this, and then labels to facade. I think it's pretty similar like this, pretty similar to this problem. And then BW to color, black and white to color, to actually colorize images. You could use it too if you have if you could train powerful networks. And then maybe change scenes, maybe turn turn in day image to a night image. For example, you took a photo in the day and maybe want to make it look as it was taken at night. You could just train a model with the data set of maybe morning and evening or night images, and then adjust a photo given, let's say, a sketch or a edge photo. You could generate it however you want. Given that image, generating a realistic image is also an application. These are pretty cool applications. Just, I mean, right? And then here, as you can see here, we can just read it. You can just read the paper. So these people have put in their efforts. I think they're from UC Berkeley University. So they have wrote this paper. So these people. So as you can read here, we will be covering some parts. Let's see. Let's see what parts we should cover. So I think we should read this, right? So the community has already taken significant steps in this direction, with convolutional neural networks becoming the common workhouse behind a wide variety of image prediction problems. CNNs learn to minimize the loss function and objective that scores the quality of results. And although the learning process is automatic, a lot of manual effort is still goes into the designing effective losses. So the problem is, I mean, definitely you could argue that we could just simply use a CNN. I mean, that's probably the first argument that will come to your mind. As a deep learning engineer, we don't have to use GAN, maybe. I mean, like, in the paper, the approach they took is they have not started with the GAN. They just like at least the sentences that they wrote, they have first started to understand this problem, but probably simplifying it, maybe using a CNN. But the path ultimately had led us to GANs, right? If you can see here, goes into designing effective losses. So a lot of manual effort still goes into designing effective losses. So essentially, the process of deep learning is, of course, minimizing a specific loss, whatever that is. So the basic idea, the basic thing, or the most important thing for us to do to solve this problem, to actually take an image and predict some changed images, maybe change some things in this image and do something, just like the examples that we have seen just before. the main idea is actually generate a loss function, right? We could definitely use CNN. We could definitely do some downsampling, upsampling, maybe unit architecture. I'm going to come to unit architecture in just a minute. So we could just definitely use CNN. But the main problem, the main effort that we have to put, the main important thing we have to give, the thing we have to give the highest amount of importance is designing effective losses. So what should our loss be, right? In other words, I'm going to study, I'm going to read it, not studying. In other words, we still have to tell the CNN what we wish to minimize, right? So we have to specify what the loss function is, which is nothing but which is probably the most important thing in any while solving any deep learning problem. But just like King Midas, okay, I don't know who King Midas is. I'll search for King Midas. Who is that? Maybe it's something that we have. Okay, okay. He's a man with high, very like maybe foolish and greed man. So yeah, what we should, but just like King made us, we must be careful for what we wish for. Okay, yeah, it is a metaphoric sentence. All right, so the idea is again, they are stressing the point that we should develop better loss functions. Right, if we take a naive approach and ask the CNN to minimize the equidistant distance between predictor and ground truth pixels, it will tend to produce blurry results. So what they are telling is, if you use a CNN, right, we should use a CNN for this type of problem. Taken an image and spit out an image. We could use upsampling and downsampling convolutional, convoluted and convoluted transpose, and we could definitely build an architecture. But the main thing we should care about is the loss function. How can we change the loss function such that the CNN performs better? Because the basic idea of deep learning is to optimize the loss function, and the better the loss function, the better the model is. So how can we use CN loss? If you use something like Euclidean distance, just subtracting the values and squaring them and all that. If you use Euclidean distance, or even mean squared error, right? If you use something like that, then I think there are two main reasons for not using like reasons for not using the Euclidean distance loss. I think the number one is because blurry results are produced, because in Euclidean distance, essentially, we will just add them up and take the mean, right? So there is taking the mean in some step. So therefore, we'll get blurry results, right? Because there are a lot of values, and definitely taking a Euclidean distance is not a very good idea. Subtracting them, adding them, and all that. That is one thing. And the other thing is, like, if you think about it, if you want a child to actually draw something, you don't want the child to actually draw the same thing that we have shown, let's say yesterday. Maybe the child saw a picture yesterday, and you don't want the child to actually draw the same picture. You want him to actually put in some more creativity, and based on all of these images, and based on all of the images that the child has shown before in his life, maybe come with something that is more creative. Maybe find some patterns and all that. Maybe different positions. I don't know, right? We don't want the pixels to match up, right? Exact position of each pixel, and different exact position. Essentially, that is what we are doing in Euclidean distance, exact position and all that. But while if we had another loss function that is better, right? We want that loss function to actually force our model to actually predict something that looks realistic. Again, we are getting to the concept of GANs. All this path, all this thinking is getting us closer and closer to the ultimate solution of all our problems currently, the GANs. So the GANs is our ultimate solution. It is leading us to GANs. Again, if we take a naive approach to ask the CNN to minimize the Euclidean distance, blurry results. This is because Euclidean distance is minimized by averaging all plausible outputs, which causes blurring. Yeah, we'll just average all the plausible outputs, coming up with loss function that force CNN to do what we really want is definitely a problem. So it would be highly desirable if we could if we could instead specify on a high level goal, like make the output indistinguishable from reality. Essentially, what again, we are getting to GANs again, the concept of GANs. We want the loss function to make the model, or to update the weights such that the output is indistinguishable from reality. Essentially, GANs, right? Training another model, discriminator, and then based on the performance of the discriminator is the loss function of the generator. So the better the discriminator, the more the higher the loss of this generator. So we'll train this discriminator. So that is exactly what will happen. So this idea has led us to generative adversarial networks. So we'll train the discriminator to actually take the image generated by the GAN and predict the probability of how realistic that image is. And that is what we'll be doing, right? So that is an essential idea. So definitely that has led to the idea of generators, right? So conditional GANs, we are not the first to apply conditional setting. So we are going to use conditional GANs, right? And then the architect, and then there is another thing. I think I'll go to the whiteboard. We don't have to read the paper. I think we'll leave it there. So again, we have came back to generative adversarial networks, and I'm going to go into the theory. Just some changes that we have done in the Pix2Pix paper. The first idea is we have in the CNN architecture. I'm going to first go through the architecture. What is the architecture like? We have used an architecture called UNet. Right, so nothing fancy. It's not a very even very new for us. So UNet is nothing but we'll have a combination of encoder and decoder. Encoder consists of convolutional layers, and the decoder consists of transpose convolutional layers. It just goes like this. So we'll take the input matrix, of course, and then we'll have CNN layers. We'll just turn this out input into what? Something like that, right? And then there is shade weights between encoder and decoder. Let's draw the diagram first. Just like residual connection, some output will be passed through. So essentially, the idea is we'll take this image. This is the image, right? What we'll do, what we'll be doing is we will be using convolutional layers, CNN layers, normal CNN layers. On this image, we'll be performing the CNN operation on this image. Hence, condensing the size of this image will be condensing this image into a very small vector or very small matrix. And then after we have get to a point where we could where the vector is small enough, we could actually based on the input, we can use another CNN layers. We could use CNN transpose to rebuild that image with some changes. So that is exactly the idea of Pix2Pix, right? Taking an image and making some slight changes, not slight, yeah, definite, absolute changes to rebuild that image, but with different but with different changes. For example, black and white image to color image, we're going to take the contents, we're going to put this image into here. We're going to have CNN layers to actually compress this image, or use CNN layers to actually get the important details. Again, the weights are optimized, right? So we are going to use these weights to actually get important details, and hopefully this vector will store the important details in this image, and it will just remove all of this unimportant image. For example, in the case of black and white to colored images, maybe it'll store the information of the objects, maybe the sizes of the objects, maybe the position of objects. The different features will be tracked, right? Different features will be stored, and then after that, after we have condensed to this very small output, we could use transpose convolutional layers to actually rebuild that image, to actually rebuild an image from that vector or matrix, right? From that output, we'll actually rebuild that image, and again, these layers are also optimized. So that is a model, pretty simple, right? Nothing new. We're going to use CNN layers to actually find some important features that can be used for that specific problem based on the specific data sets and on the specific loss function and the data set on which the discriminator is trained on. And then we are going to update all of these weights again. So we are going to regenerate these images. We are going to regenerate the image with the required changes. So that is the idea. If UNet, right? the name, I think the name come from this. So essentially, if you draw it, like if you look at unit architecture images, it essentially get a shape of U. So maybe that is why they have named it as unit. Yes, that is we have used unit. Again, another change is we're going to have residual connections. That we are going to pass the gradients or pass the outputs to from the encoder layers to the decoder layers. Maybe in the encoder layer, we are just going to get the gradient outputs. We're just going to get the outputs and input them to this. We're going to input these outputs to this um, to the layers of the encoder layer, such that we will be such that we will escape from the problem of vanishing gradients, right? Forgetting the important things, right? So vanishing gradients is of course a very famous problem, and ResNet, just like ResNet, will be using residual connections from encoder to decoder to actually not to solve the problem of vanishing gradients, to give the required importance for everything. And then another change that we'll be doing is the discriminator's loss function, right? In the discriminator's loss function, we're going to have this normal discriminator loss function. I'm going to say t loss, which is of course going to be this prediction of like to update to update the model, to update the layers of or the weights of the discriminator. We're going to have a loss, which is nothing but a like just like I'm going to go through that part. I'm going to go to that part just so you can understand. So we are going to have a normal MSE, mean squared error, between for to update the loss of this equation. Okay, so to update the loss of this equation, generator. So we're going to have this generator, right? To actually update the loss of generator, we have the generator loss again, and after we just now, and with the generator loss, we're going to have the G loss, and then we're going to have we're also going to add the L1 loss, right? The L1 loss stands for mean squared error. We're also going to again, with the generator loss, we are also going to have mean squared error loss, just so that we could just like not just like make them precise. Like we don't want the model to be too creative. We don't want the model to actually just be creative, because in this problems that we are solving, Pix2Pix problems, image to image translation problems, we don't actually we don't right we do not only want the model to actually generate new outputs, creative outputs, right? We also want the model to actually be precise, like be maybe get more a high quality image. That's why I use element loss to actually like just get the mean squared error for the input to actually be as close as to the output. So therefore, the combined loss function, this combined equation, will be updated for the generator, right? I'm going to go through, and then generator with skips, and then again the another new idea is patch GAN. Patch GAN is introduced. So what is patch GAN? I'm going to go through that. What is patch GAN is, right? So while training the discriminator, right? Rather than having, for example, this image is generated by the generator, right? For example, we give the generator the noise and the maybe the label, right? Conditional GANs, right? Maybe we get this image, right? So what we'll be doing is, while training the discriminator, we'll be creating patches. Maybe like say 4 patches, let's say. So we're going to take this patch, take this part of this generator image, we're going to pass that to this discriminator, and then we're going to do the same for all the models. So essentially this is right, this is the discriminators. Everything is same. I'll probably change this diagram just for your understanding. So I'm going to give all of these values to the discriminator. So what we'll be doing is, for each 1 2 3 4, so for each patch we are going to use the discriminator. For example, the first patch, for the first part of this image, we are going to give this part of this image to the discriminator, and the discriminator is going to predict a probability of how realistic that part of that image is, right? So for example, the generator predicted image, right? So for each part of that image, we are going to predict how realistic that part of that image is, and we're going to do that for each patches. For example, we're going to have this patch, right? So we're going to, let's say, have this shifting box, maybe shifting kernel, just like kernel. We're going to shift this through all of these values of this matrix, and we're going to uh, use this discriminator to actually predict how realistic each part is, and then we can just average all these values out and maybe get this final output of how realistic, the probability of how realistic the whole image is. So what these the actual benefits of using this? Well, number one, if you have an image with like, for example, when training the models for like 4K images, very high quality images, the discriminator might or not actually find smaller, maybe smaller things that should be corrected. Maybe let's say there is very small part of this image that is not realistic. Maybe a generator needs to update this small part. If we train the discriminator, if we give the discriminator the whole image, the discriminator might not actually give a very high gradient or very high importance to this part. Hence, the generator might not actually update this part. But if we add patch scans, we could give a more importance and maybe higher quality images, looking at every single thing, right? So that is one advantage, and other advantage is, of course, sharing weights. We have shared weights. We don't actually have to like get a higher amount of CNN layers or higher amount of CNN kernels. Whereas here we could just have a little lower or a little smaller CNN, and we could just use this smaller CNN for all of these patches. So that is idea. That is the idea of patch GANs, having these patches again in the discriminator. So I think those are the those are the biggest changes we have. So as you can see here, we have inputs. I mean, like there are some experiments that are done. So these are the inputs and these are the outputs. So this is the input and this is the ground truth. Ground truth being the actual output that we want our model to predict. So if we train the CNN with just pure L1, with just pure MSE, mean squared error, as you can see, the images are quite blurred, right? So you have very blurred images. Everything is blurred here. Like, yeah. If you train the model CNN on just MSE, mean squared error loss, we are going to get these outputs. If we use this conditional GAN with no L1, right, we are going to get outputs like this, right? If we use a model, just like I have told you in the last video, we're going to get some outputs like this. And if we use a conditional GAN plus L1, if in the discriminator, in the generator, if you add L1 loss also, then you're going to get values, images like this, which is maybe better, maybe not. Maybe some images are better and some are not. And that is the thing, right? So that is why we use L1 loss also. We add L1 loss to this GAN, and then that's it, right? Again, so we have many data sets here. You could just check, right, how good the images are, the predicted images are. Yeah, background removal also. You could use it like for any problem that involves like image to image. You could do it. Maybe there is some information at one image, and then you want to copy it, but with different features, you could definitely use it, right? And then yeah, so that's it. So I think those are the main changes that we have. And then let's code it. We are not going to code it. There is actually a very good article by the official TensorFlow documentation. Right. So there is TensorFlow documentation. From TensorFlow documentation, there is official page. So there is an official document of actually developing this model. So the dog is barking outside, I think. So yeah, there is this official implementation. We could actually use it, right? I mean, you could also run it if you want. I mean, you could run it if you want to. So I think I'm just going to go through the code, right, along with some more informations. So first we'll going to import TensorFlow, OS, pathlib, time, datetime, matplotlib, and IPython, right? And then we'll use this data set. I think the data set actually is segmenting, yeah, segment to actual image, right? So from the segmentation image to actually the actual image. So that will be the problem that will be solving. So yeah, this is the URL for the data set, right? And then you could just use this function to actually get that data set and use it and maybe store it in your current environment, right? And then we'll use this function to actually read the data set, right? Just to get one sample image. So this is one sample image, and then we'll build a function to actually read all the images of this data set, right? And then we'll just build a bunch of functions. We'll build a bunch of functions. Resize function. First, we'll build the resize function to actually resize the input, right? To resize this input image. So, and then yeah, essentially what we're going to do is we're going to take the input image, and then yeah, we'll just resize it to the near to this 256 to 256. So maybe we have a larger image, we're going to compress it into 256 by 256 image, and then we're also going to do cropping. We're going to crop a specific part from that image based on the image height and image width to again 256 by 256, and then we're going to normalize these values from to make sure that every pixel is in the range of -1 to 1, right? And then we're going to have and then we're also going to perform, wait a minute, right? I'll try to talk as slow as possible because yeah, the neighbor's dog is barking. I don't know why, but I mean, let's go through it. So again, we're going to resize the values into 286 by 286, and we're going to crop them back into 256 by 256 just to make sure the model is actually comfortable with both with images in different positions and in different maybe in different sizes, maybe big or small, right? For that, we're going to do that, and then we could just inspect. We could actually see these images. So we're going to use this function. We're going to use this random jitter function that we have just built here. So in the above section, so we have build this random jitter function. We could actually use it on some images, right? And then we could just experiment them. We can just see these are the outputs we get. So essentially, we have them. We have flipped them right here, and I think yeah, here we have flipped them this side and this side. We have like if you can see here, the image is more towards the left, and here the more image is more towards the left, right? So and then we'll just do some cropping just to make sure the model is actually comfortable with images at different positions and all that. And then we'll just create this function load image train to actually load the training images. So we'll call the load function that we have built here. So we have built the load function here upright, and we also call the random jitter function that we have built above. We'll also call the normalize function, and we'll perform all of these functions on the image, right? And then we could just give the input image and real image. Input image being the X, and the real image being the Y. And after we do that for both test images and training images, we'll build a function for both of them, right? Here in the testing images, we could actually resize them. We would actually resize them because while testing, maybe we get image from like if it while training, here we have images of same sizes. While testing, maybe you have images of different sizes. Maybe you collect images from internet. Maybe you could just use this. That's why we add this additional function to actually resize the values. And I think we will not be adding all of these values. We are not going to crop the training testing images, right? We are going to perform all this cropping and all that on training images because again we want to train the model on. That will be useful for only for when training the model, and while testing we don't actually want to crop the images and do all of these things because because we are just testing, right? We'll definitely have images of different data distribution. So therefore we'll only be performing random all the image pre-processing for training images. And after that, we could actually build a data pipeline using TensorFlow data set. So we'll just call this data set on this image files. So we'll just take all these image files and call this function. We could actually create the TensorFlow data set. And then what we'll do is, on this training data set, after we have created this training data set, we'll map this data set to this image data train, load image train function. So we have this load image train function above, right? So what we're going to do is, we're going to take this load image train function and apply this function to all of these images containing in the training dataset function or training dataset. And then we'll just shuffle these values and create batches to do batch wise training. And then we'll do this. We'll map the dataset for both test set also, and we'll also create batch sets for test sets. And then right, and then we are also going to do some checks to actually see if the values exist, right? If we use the name test or val, this is not actually important, very important, just for checking if the name is correct or not, whether it is test or val. And now we have done the data pre-processing. We have pre-processed our data to actually be now we could actually train our model, right? So now we can actually build our GAN and train our GAN and maybe get some very good results. I mean, let's try what type of results we'll get to, right? So first what we'll do is, we'll set the output channels, right? So as we are doing RGB images, we'll be needing both red, green, and blue channels. So we are essentially going to have R matrix and G matrix and D matrix containing images, right? And values for how intense that red pixel is for the red channel, right? So now we're going to build a function called downsample, which takes in filters, size, and then the apply batch norm is equal to true. So whether you want to apply batch normalization or not, right? So I'm going to say, first we are going to create this initializer, tf.random normal dot initializer. So to actually initialize our weights, before training. And then we are going to now create our sequential layers to actually train our model. We are now actually going to create the layers of the downsample when we want to call downsampling convolution. So in the unit, we're going to have downsample layers and upsample layers, the UE architecture. So when we want to build the downsample layers, we are going to use this function. So I'm going to call this method to actually create models. I'm going to add these layers. I'm going to add the CNN layer. I'm going to first add the CNN layer, and as we are building the downsample layers, we could just use the convoluted, no need of using convoluted transpose. And then if apply and batch norm is equal to true, which if we don't touch batch norm, we're going to add batch norm. So when building, if you want match batch norm, we'll add a batch normalization layer, and we'll also add a DQLU layer, and that will be the output. We'll return this result, right? We could actually call it to actually see if the shapes match. If they do match, it's 128 by 128 by 3, the output image size. And then so this is essentially the encoder layer. Now let's build a decoder layer or decoder. I think it's a decoder layer. I think they are going to use multiple upsample layers. So we are going to see the decoder layer, not the complete decoder. So we are going to have upsample, right? After we have downsampled it into a for a specific amount of times, for a number of times, we'll upsample that images. And then we're going to have we're going to build model again. We're going to have sequential, and here we are going to use convoluted transpose to actually upsample our images. We're going to take lesser image matrices of lesser dimension and map them to matrices of higher dimension to actually generate that image. And then we're going to have filter. We'll input all the images, all the parameters: filter, size, strides, padding, kernel initializer, and use bias. We are not going to use bias, the addition term. And then we're also going to add batch normalization And if we want to apply dropout, which will also be a parameter, we'll add a dropout of 50%. We're going to drop all the 50% of neurons in the previous layer, and then we're going to add the reliever function, which will be the final output. So again, we could actually see if that works. So the output image. So if you can see, observe here, the output dimension of downsample will be 128 by 128 by 3, 1 by 128 by 128 by 3. 1 represents batch size here. And then the output of upsample will be 256 by 256 by 3. So we're going to take in a 256 by 256 by 3 image. We're going to, right? So we're going to take in 256 by 256 by image into this downsample layers, and the output will be 128 by 120 by 3. And after performing this for a specific amount of times, we'll get to the upsampling layer, and the output will be 256 by 256 by 3. Right? And then we could actually do it. Now let's build the generator. Right? A specific amount of, like, we're going to have number of downsample layers and upsample layers. So we could actually create this function called generator. And then we'll take the input. The shape is 256 by 256 by 3. We're going to take an RGB image that has 256 neurons in the image width and height section. So first we're going to create the down sampling layer, which is represented by this list here, down stack. And then we're going to have up stack to actually build the encoder. So this is the decoder, by the way. Sorry, this is the encoder. So we're going to have number of downsample layers. We're going to have these many number of downsample layers. We're just going to call this function that we have built here in the previously downsample function with the parameters, with the amount of parameters, right? And then we're going to have upsample layers with these many upsampling layers, and then we'll get the output. And we're going to have the last convolution to the transpose layer just to make sure the outputs match. So yeah, if you can see here, that is the beauty of TensorFlow documentation. You have sizes of each matrix after the output. For example, after performing the first downsample of the encoder, the output will be 128 by 128 by 64. And after performing that, see, the output is actually shrinking down the output to actually 64 by 64 by 128, 32 by 32 by 256 to actually 1 by 1 by 512. After the final downsample layer after encoder. So after in the last layer of the encoder, the output will be of shape 1 by 1 by 512. That will be the final shape. So this 1 by 1 by 512 matrix will hold like 512 vector will actually hold all of these values of like the relations and the main patterns that are found in this input image. And then after performing the first upsample layer, the output will be 2 by 2 by 1024. And then after performing the next upsample layer, we're going to double that, 4 by 4 by 1024, and then 8 by 8 by 124, and until we are going to keep doubling the output sizes until we get to this value of 128 by 128 by 128. And after here, we could actually we should, just to make sure the outputs match, just to make sure the output will be actually 256 by 256 by 3 matrix. We'll have the final convolutional truly transpose layer, the final one, right? With the output channels being 3, right? 4, I think 4 is the size, number of kernels, strides, initializer, tanh. And after performing this final transpose layer, the output size would be batch size by 256 by 256 by 3, which would be the output image. So this is be the output image. So output of this final layer will be the image. And we could actually add skip connections here, right? So after we would just go through the down layer, right? And then we would add that to skips, and then we'll just reverse it and maybe and concatenate them to these layers in the down, like in the decoder. So we'll just take this value of the encoder layer, so as a specific value of this encoder layer, and then we'll just get them and add them to this output of the decoder layer. So we would, this is essentially the residual connections. So we are going to have a for loop that loops through this down stack, this list. So we're going to loop through that list, and then we're going to perform this, and then we're going to have skips to actually append all of these x values. at least all of these X values, and then we're going to get the last value, right? Sorry, I think we're going to get, this is the first value, right? No, not the first value. Like all the values and except the last one. We're going to get all the values except the last one, and just going to concatenate and just concatenate them at a specific layer, and at every time. So at every time when we are doing upsampling layer, we are going to concatenate this skip, and then zip function to actually like it is. I'm going to show you the diagram just to see, just show you how it works. Right, so we're going to have the decoder layer, right? So in the decoder layer, we're going to have the number of values, and then again, this is the encoder layer. So what we'll be doing is, so essentially this value will be adding to this will be adding to this will be adding to this will be adding to this. Sorry. So this output will be adding to this output. This output will be adding to this output to this output, and that is why we should use the zip function to actually get to loop through upstack and skips, right? So we're going to go through all the upstack values and the skips, and then we're going to add all of these values or concatenate all of these values, and we could actually see plot using this. I think a relatively new feature of TensorFlow. Maybe it is pretty new, right? So to actually see how it works, just as I tell you, we are going to add all of these values. We don't have skip connections, right? That is a skip connection. You can actually go through that image for some time, right? As you can see here, as I have told you. So this is the. Can I zoom out maybe a bit? I'm just zooming out just for now. I know you probably cannot see anything right now, right? So yeah, so we're going to add this value. So so this is the encoder. So that is why we don't have CNN layers. We're going to downsample these images, and then this is the decoder. As you can see here, you get the shape of U, right? Maybe that is the reason we have the name is unit. So we're going to add these values, add the value of the encoder to actually the decoder. So we're going to have a sequential manner of adding. We're going to sequentially add all of these values. So this value to that, this value to that, and this value to that, and all that. Right. And then now that we have developed the generator, we can actually test it on some random noise to actually see if that works. Now let's build the generator loss. Right. So as I've told you, we will be making one change. We'll also be adding L1 loss, the binary cross entropy loss, right? And then yeah, just like here. So we're going to get the GAN loss. This is nothing but loss object. We're going to perform binary cross entropy on ones, like on all the ones, matrix of ones, and the disk generator output. And after that, as I've told you, we will also be adding L1 loss, which is nothing but the mean squared error or reduced mean here. So we're going to have we're going to get the difference between target and generator output, right? What is the actual output and the generator output? So for each pixel, we're going to subtract all these pixel values, and we're going to get the absolute value. We're going to like square them and get the square root again, and then we could just build the MSC loss function. And then after that, the total generator loss function would be nothing but GAN loss, this loss, plus the lambda times L1 loss. So lambda will be I think a constant that specifies how much importance should we give for MSC loss, right? If you want the image to be of higher quality and give more importance to little features, maybe the lambda should be a bit higher, such that when in terms of gradient descent, more importance is going into L1 loss. So as you can see, this is this architecture, the final architecture, or the overall architecture of GAN. Now let's build a discriminator. Pretty simple, right? So we're going to have right. So yeah, so we're going to have input shape, target shape, right? Target image shape, right? We're going to concatenate all of this input and target. We're going to take this input and target and concatenate them. And then we're going to have a bunch of downsample layers, that the layers that we have built previously for GAN, but we are going to use the same layers for here also. because we don't have to build them again. And then we are going to add padding, CNN layers again, the final CNN layer to actually get the output. And then normalization, ReLU, padding, and there is another CNN layer. Okay. All right. And then we'll have the final output. So where is the output finally? So yeah, sorry, I forgot, right? Yeah, again, I'm really sorry. We are using PatchGAN. I totally forgot it. As we are using PatchGAN, the output will not be a final dense layer. It will be an image like this. So this will be the output of the discriminator. So for each patch, we're going to use relatively very small patches. Like we're going to take very small patch and we're going to predict how realistic that small patch is. And then we're going to get a value something like this, specifying how realistic that part is, how realistic that part is. Maybe, yeah, maybe higher values define higher amount of realistic it. Like maybe the values are high amount of realistic, very high realistic, highly realistic. Again, we are not going to use any sigmoid function here because we are going to follow the thing that we have done in the previous, that we have learned in the previous video. We're going to use this Lipschitz theory, right? We're going to not that, right? Yeah, so no, we are going to use a constant, critic rather than a discriminator. We are not going to predict the probability, but how good that prediction is, right? So we're going to perform this. The output will be a convolutional layer. We are not going to have a dense layer because we are doing perform PatchGAN, right? I totally forgot. I'm telling you, really sorry for that. Right, and we could just test the discriminator on random noise. And then now let's give the discriminator loss. Now let's build the discriminator loss, which would nothing but real loss per generated loss. And then we could just return the total discriminator loss. Now let's define our Adam optimizer. Again, we are going to use the same for out generator and the discriminator, essentially. And then we'll create checkpoints to actually save the model at specific times of the epoch. I think I'll cover more of TensorFlow in the future videos because there are a lot of functionalities pretty new functionalities in TensorFlow that maybe I have not known about. Right, I have been using TensorFlow for a while now, but still everything is changing. Maybe I should keep up with the documentation. Right, so you can just create checkpoints to actually store this model file at each epoch to actually see based on the performance, of course. And then now let's build a function to actually generate images. Take the generator and generate images, right? Display images. So yeah, we are going to take the model also. We're just going to give this model the images and then put training equal true, because while training we should generate the images, right? Generate the images, train the discriminator. To actually train the generator and the discriminator, we have to generate images. So therefore, I'm going to set training equals true. Then to actually display the images, maybe when we want to, yeah, we are displaying the images for while training. So therefore, we'll have this. We'll display the image while training also. And then yeah, here we are creating checkpoints to create logs to actually see how our model is actually performing at each step. And finally, there we go. We have the final training loop. I'm going to cover training function. So this is all of this happening at each step of training. So we're gonna have we're going to set the gradient tape and for both generator and discriminators. And then we're going to call the generator. First, we're going to give this generator the input image. We're going to get this input image, pass that to the generator, set training equals true, and then take this output, generate output, which will be image, and pass that to this discriminator, the input image and the target. Wait a minute. So yeah, we're going to put the input image and target for the realistic images. So we want to train a discriminator for both real images and fake images, right? So we'll pass in the input image and the target, right, to see if how well it performs. And after that, we'll give it the input image and the generator output, which will be this output, to actually see how it performs. And again, we'll calculate the loss for both generator. So first we'll perform the calculate the loss for generators, and then we'll calculate the loss for discriminator, and we'll use the gradient tape to actually update these values. Right, we'll update these values and apply gradients. We'll apply gradients to update all of these values. Right, again, we are not going to follow the method that we have used in the last video to actually train the critic 5 times more than the generator. We're not going to follow that for now, but yeah, you get the idea, right? So we're going to update all of these gradients for both gradients. We're going to update the gradients and trainable variables. So as you can see here, we're going to use this zip function to actually match. Like, zip function is actually used to match all of these values, like for each gradient and for each training variable. Right, we're going to calculate a bunch of gradients for each training variables, and we're going to zip these values such that we could match up all of these values to update these parameters or trainable variables. And then we could just create the final training loop, everything that happens in one training loop. So we're going to use a time function to actually measure how much time it took for each step, and then yeah, you get the idea, right? And then yeah, you get some images like this after training for 39,000 steps. After training for 39,000 steps, if you are Google, you could train it. Or if you are you have powerful maybe computers, you can train it. I think I'll try to buy Google Collab subscription maybe for 1 month, like maybe for maybe after some maybe in the month of August. I'll probably, after we have like 30 projects, like we have built many models that we want to train, right? We have built the neural machine learning translation and question answering model. We have built text summarization model. We have developed the GANs, like normal GAN, conditional GANs, consistent GANs, and here now we are going to build Pix. We have built Pix2Pix back GANs. So maybe in one fine month, I'll probably buy the Google Collab subscription. Probably cost around 700 rupees per month. I'll try to buy maybe, and then we could just train all these models, because I mean, like, how long will we just sit down and just how long will just stay quiet rather than training on models? Maybe I'll try to buy the Collab subscription. Then we could just I'll try to upload maybe 2 videos a day. I don't know. I mean, just first we'll collect a lot of, maybe let's train our own YOLO model. I mean, we could train them, right? So yeah, so coming back to context, that's it. This is the Pix2Pix GAN. Hope you understand everything that's going on here. Actually, image to image translation, taking an image, transforming it into another useful image, and actually train this in things. So I'll provide the I'll provide the link of this and this. So I'll provide the link of this document and the research paper in the description. Thank you for watching, and I'll see you in the next video. So yeah.